A hardware-accurate digital twin, when coupled with manufacturing correlated modeling via a process design kit, PDK, becomes a manufacturing correlated model of the microelectronics. The combination provides the basis for meeting all the criteria necessary to ensure that the model will match the manufactured part. PDKs are a formalized method the semiconductor industry uses to ensure first-pass success of new designs. PDKs are correlated and thus specific to a specific process manufacturing line. This coupling expands the role of the HADT from functional to multiphysics analysis. Example: thermal, reliability, signal integrity, electromagnetic emissions, and security side channel testing. The commercial system on-chip society design ecosystem evolved a rigorous virtual sign-off process. It includes the use of hardware-accurate digital twins. This minimizes long, costly physical prototype loops and enables shift-left, look-right process deserialization, which is useful for microelectronics design and lifecycle support. As a part of the education process, the model-based systems in engineering think they have a whole model of the system, but it is abstract, and you can't verify everything from that model, so they need to be educated on the gaps in their methodology. As we explore the concept of digital twins, it's essential to recognize that not all digital twins are created equal. Each has its unique abilities, such as abstraction levels, execution paradigms, and more. However, a common gap in some system development is the connection to the details of the hardware and manufacturing process. This is a critical oversight, as clock cycle accurate, bit accurate models that are correlated to manufacturing are necessary for ensuring correctness. These details are not just nice to haves, they are critical to the success of the project. Ignoring the abstraction gap between the digital twin and the physical system can lead to predictable types of failure, which can occur regularly. In fact, neglecting the abstraction gap is a recipe for failure. By not accounting for the intricacies of the hardware and manufacturing process, you risk introducing errors and inaccuracies that can have far-reaching consequences. So, what does this mean for your system development? It means that you need to prioritize the creation of digital twins that accurately reflect the physical system, including its hardware and manufacturing details. By doing so, you can ensure that your digital twin is a reliable and trustworthy representation of the physical system, and that you can avoid the pitfalls of predictable failure. As we design complex systems, it's essential to ensure that our models accurately reflect the manufacturing process. Unfortunately, many MBSE models today are not correlated to the manufacturing process, leading to potential errors and discrepancies downstream. The traditional MBSE approach often results in a design-to-test paradigm, where the design is created without consideration for the actual hardware implementation. This can lead to a mismatch between the design intent and the manufactured product. What's the solution? We advocate for a hardware-accurate approach, where the design is created with the actual hardware implementation in mind. This means that what you design is what you get. The design is accurate, and the manufactured product will match the design intent. With a hardware-accurate model, you can perform software verification on a digital twin of the actual hardware. This gives us confidence that both the hardware and software will function correctly when the system is assembled in the lab. When creating a hardware-accurate model, we need to consider several key factors. First, we need to ensure that the timing of bits is accurate, including latency. This requires identifying hardware timing to ensure software correctness. We also need to perform negative testing to ensure our design can recover from errors. This involves simulating error scenarios and verifying that the system can recover correctly. Another important consideration is using actual data rather than virtual data packets. This means using actual resolution and accounting for actual hardware data type accuracy limitations. Finally, we need to consider the sequence of bits, including communications handshake protocols. This ensures that the system can communicate correctly with other components and systems. In conclusion, a hardware-accurate MBSE model is essential for ensuring our designs are accurate, reliable, and functional. By considering these key factors, we can create systems that meet our design intent and perform as expected in the real world.